Hey everyone, it's been a little while since I gave you an update on my house, but I thought I'd take you through the next part in the design process. If you recall, the first two videos had to do with my manual J load calculation and then my manual S system selection. Now we're going to get into the third part of the ACCA design process, which is the manual D duct design. And you can't really do manual D unless you start off with a load calculation. That's going to give you your CFMs, and then a systems selection. You got to know what your blower can do, and only then can you actually match the proper duct system to your equipment and to your project. So why don't I show you what went into my project? We start off with the basic floor plan of the house. Remember, the house is on a slab, so everything will need to be in the attic, which, as you recall, is spray foamed at the roof deck. The attic access typically goes here on this model plan, in the master closet. This allows the air handler to be close by, on a platform. I like the idea of keeping returns close to the air handler and at a side of the living room or main entry for aesthetic purposes if possible. Our goal is to design a duct system that delivers the air as efficiently as possible to the supply outlets while keeping branch lengths short. It's very important to control room pressure, especially when you design a single central return. And let me explain why. Let's imagine what happens to the bedrooms when the doors close. Typically this happens at night. If there are no returns in these rooms, that means we're supplying air to these rooms and building pressure in them. Now that air wants to escape these rooms and it has very few paths out. Usually door undercuts are not large enough to relieve that pressure and allow enough air out. Now this is especially true in the master suite because there is a bathroom and several closets that are behind that door as well. So in this case, it totals 4 supplies. All that air wants to escape somehow, and it will take all paths, including the small gaps and seams in the building envelope, and exfiltrate out. An even worse problem is the main area in the house, which has all of the return, but not nearly enough supplies. The exact opposite will happen. The main area will depressurize and start leaking hot, humid, dirty air uncontrolled into the space. And now this is why a lot of houses are uncomfortable, because these room pressure imbalances drive bad air into the house. So what is the solution? Jumper ducts. These can be considered as an unconnected return. These are ceiling grills that are in each room, similar to a small return that connects to a small diameter duct, and the other side of that duct connects to another ceiling grill in the main area. This allows a return path out of the room and back to the main area where the central return is, and you avoid having to run a dedicated return to each room. It accomplishes the same thing as individual returns, but with less ductwork in the house, resulting in lower static pressure, better performance, and lower material and labor costs. If your project allows you to use 1 or 2 central returns and jumper ducts for the rest of the rooms, I strongly advise that you use that strategy. But then my builder informed me that they would not be able to put the attic access in the master closet for framing purposes. The only other suitable location would be the mudroom, which would take up the space that I had planned to put my central return. This means that I had to move the return to another tucked away place, in this little hall by the bedrooms. It would still be visible from the living room since there is a case opening between the living room and the hall, but you can't see it from the living room. And that was kind of a bummer to have to move it, but these things happen in residential construction. Because I was moving the central return to this hall, I wasn't going to get that short return that I was hoping for. This would add a significant amount of duct length, thus friction and static pressure to the system that I was going to have to design around. Fortunately, I found out about this before I had finalized my duct design. And there really wasn't any point to have jumper ducts in the smaller bedroom, because my return was going to be right there just outside of those bedrooms anyway. I would just connect these small returns to the main return box, using it sort of like a plenum or a collection box. Then there was another problem, this time with the supply. Since the family room ceiling has a 14-foot peak and the roof deck was getting spray foamed, there would not be any great way to deliver air
to this supply register. This would have to move to the other side of the family room, which would present a challenge delivering conditioned air to the opposite side of the room. Since I was already running returns, I went ahead and planned for a dedicated ducted return in the master suite, since that run would be shorter than the main return anyway and would not add any duct friction. Let's go back to that problem where I needed to deliver air from one side of the family room to the other side, where I wasn't able to run a supply branch to a register. Here's some dimensioning: 14 feet high at the peak and 18 feet wide. Now I need to be able to throw that air approximately 16 feet. The typical supply register that you find in a supply house can't do that. But commercial quality supply registers can. They have engineering data, and they're designed to throw air farther. All you got to do is look it up and then do the math. Now this register would be throwing around 105 CFMs. And according to the data, a 6x10 register, one-way diffuser, at 125 CFMs will throw that air around 16 feet. So that was perfect. Register selection and placement is a very important step of duct design, and it often gets overlooked. Now, I think this has to be done before the ducts are sized, since the register throw dictates the register placement, which is what you need to finalize before you can figure out what your total effective length is. You can't size ducts before you do any of this, so it often gets overlooked, but it shouldn't. Now I had everything I needed to design my duct system. I modeled my house in RightSoft, which gave me my load calculation already. Now, RightSoft is powered by the ACCA manuals, and Manual D is for residential duct design. In my previous video about equipment selection, I showed you how I arrived at my decision to use the Bosch 3-ton air-to-air heat pump. My load calculation gave me my target airflow CFMs, and my system selection showed me what my static pressure would be at using that air handler to achieve that target airflow. I never designed a system, though, to achieve my target airflow at its highest fan speed, since it leaves you nowhere to go if you still need some more flow. I entered all the performance data into RightSoft, then I entered in my component losses. Now these are airside devices like grills, registers, dampers, coils, filters, etc. that have a pressure drop assigned to them. Now the ones that apply to our system have to be subtracted so we know how much available static pressure we have left to design the rest of the duct system around. Once this is done, RightSoft figures out what my friction rate is. And this is what it will use to size the ducts, not some arbitrary rule of thumb friction rate that many of us grew up in this industry hearing. Then I drew my duct sketch on RightSoft. It automatically sizes the ducts according to my inputs. It accounts for the differences in flex versus hard ducts, and Manual D's maximum velocity limits for supplies versus returns. This is the duct plan deliverable that it displays, and I would use this plan to order materials and start my installation process. Now there's plenty more about that coming up in a future video. For now, thanks for watching. Leave any questions and comments below, and we'll see you next time.